PIN insulators and surge protectors serve distinct functions in electrical systems. PIN insulators primarily provide electrical insulation, preventing current leakage between conductors and grounded components. They are designed to withstand normal operating voltages and isolate the primary conductors from the transformer and ground. In contrast, surge protectors, also known as surge arresters or suppressors, are designed to absorb transient voltage spikes and protect equipment from damage caused by surges. They do not provide insulation in the same way as PIN insulators. PIN insulators do not suppress voltage spikes. Surge protectors do not insulate conductors. In the context of a transformer installation, the PIN insulators in an older design would not have provided any surge protection. The new design, incorporating surge protectors, offers a more robust defense against voltage spikes, which is particularly important for transformers connected to overhead lines. Overhead lines are more vulnerable to lightning strikes and other transient events that can generate high voltage surges. Surge protectors are highly recommended for transformers connected to overhead lines. They help protect the transformer and other equipment from damage resulting from these surges. To elaborate further, let's consider the specific roles and characteristics of each component. PIN insulators, typically made of porcelain or glass, are designed to physically and electrically isolate conductors from supporting structures. Their primary function is to prevent current from flowing where it is not intended to flow, ensuring that electrical energy is properly directed through the circuit. The design of a PIN insulator includes a specific shape and material composition that provides a high level of dielectric strength, meaning it can withstand higher voltages without breaking down and allowing current to pass through. Factors that influence the performance of PIN insulators include the material used, the shape and size of the insulator, and environmental conditions such as temperature and humidity. Over time, insulators can degrade due to factors like contamination, physical damage, and electrical stress, which can compromise their ability to provide adequate insulation. Surge protectors, on the other hand, are designed to respond to sudden increases in voltage that exceed the normal operating voltage of the system. These voltage spikes can be caused by lightning strikes, switching operations, or other disturbances on the power grid. When a surge occurs, the surge protector diverts the excess voltage away from the protected equipment, typically to ground, preventing it from reaching sensitive components and causing damage. Surge protectors typically use components such as metal oxide varistors, also known as MOSFETs, or silicon avalanche diodes, also known as SADs, to provide this protective function. These components have a high resistance under normal operating conditions, but when the voltage exceeds a certain threshold, their resistance drops dramatically, allowing the surge current to flow through them to ground. It's important to note that surge protectors have a limited lifespan and can degrade over time, especially after repeated exposure to surges. Therefore, it's essential to periodically inspect and replace surge protectors to ensure they are functioning properly. When selecting surge protectors, it's crucial to consider several factors, including the voltage rating of the system, the expected surge current levels, and the type of equipment being protected. Surge protectors are available in a variety of configurations, including those designed for whole house protection, individual circuit protection, and specific equipment protection. The installation of surge protectors should be done in accordance with manufacturer's instructions and relevant electrical codes to ensure proper operation and safety. Now, let's delve deeper into the specific scenario of a 300 kV amps, 3-phase 12.4 kV primary 208/120 volt transformer installation. In this type of system, the primary voltage is significantly higher than the secondary voltage, which means that the insulation requirements for the primary side are more stringent. PIN insulators are commonly used to support and insulate the primary conductors as they enter the transformer enclosure. The surge protectors are typically installed at the point where the underground primary cables connect to the overhead primary lines, often near the drip loop. This location is chosen because it's the point where the system is most vulnerable to lightning strikes and other surges that can propagate along the overhead lines. The surge protectors divert the excess voltage to ground, preventing it from traveling down the underground cables and damaging the transformer or other equipment connected to the system. The choice of surge protectors for this application depends on several factors, including the expected surge current levels, the voltage rating of the system, and the type of grounding system used. It's important to select surge protectors that are specifically designed for use in three-phase systems and that have adequate capacity to handle the anticipated surge currents. In addition to surge protectors at the primary connection point, it may also be beneficial to install surge protection on the secondary side of the transformer, particularly if the secondary conductors are also exposed to overhead lines or if there are sensitive electronic devices connected to the secondary distribution system. Surge protection on the secondary side can help protect against surges that may originate from within the building or from other sources on the secondary distribution system. The combination of PIN insulators for insulation and surge protectors for surge suppression provides a comprehensive approach to protecting the transformer and associated equipment from electrical disturbances. The PIN insulators ensure that the normal operating voltage is properly contained and that current flows only where it is intended, while the surge protectors provide an additional layer of defense against transient voltage spikes that can damage or destroy equipment. In summary, while PIN insulators and surge protectors both play important roles in electrical systems, they serve different purposes and provide different types of protection. PIN insulators provide electrical isolation, preventing current leakage, while surge protectors absorb voltage spikes, protecting equipment from damage. Therefore, in the described scenario, the new design with surge protectors is indeed more robust and provides additional protection against voltage spikes compared to the old design that relied solely on PIN insulators. To further illustrate the differences, consider the analogy of a water system. PIN insulators are like the pipes that contain the water and direct it to its intended destination. They prevent the water from leaking out and causing damage. Surge protectors, on the other hand, are like pressure relief valves that open when the water pressure exceeds a certain level, preventing the pipes from bursting. In this analogy, the water represents electrical current, the pipes represent conductors, and the pressure represents voltage. The PIN insulators ensure that the current flows through the conductors without leaking, while the surge protectors prevent voltage spikes from damaging the conductors or other equipment connected to the system. Furthermore, it's important to consider the relevant electrical codes and standards that govern the installation of transformers and surge protection devices. These codes and standards provide specific requirements for grounding, bonding, and surge protection to ensure the safety and reliability of electrical systems. In the United States, the National Electrical Code, also known as NEC, provides comprehensive guidance on electrical installations, including requirements for surge protection in certain applications. The NEC specifies the types of surge protection devices that are required, the locations where they must be installed, and the methods for grounding and bonding them. Compliance with the NEC is essential for ensuring the safety of electrical systems and for preventing electrical hazards. In addition to the NEC, there are also industry standards developed by organizations such as the Institute of Electrical and Electronics Engineers, also known as IEE, that provide guidance on surge protection design and application. These standards cover topics such as surge testing, surge protection device selection, and surge protection system design. Following these standards can help ensure that surge protection systems are properly designed and installed to provide effective protection against voltage spikes. To provide some specific examples, let's consider a few common scenarios where surge protection is particularly important. Firstly, in industrial facilities with sensitive electronic equipment, such as programmable logic controllers, also known as PLCs, variable frequency drives, also known as VFDs, and computer-controlled machinery, surge protection is essential for preventing downtime and equipment damage. These types of equipment are particularly vulnerable to voltage spikes, which can cause them to malfunction or fail completely. Secondly, in commercial buildings with extensive data networks, surge protection is needed to protect network equipment, servers, and other electronic devices from surges that can disrupt communications and cause data loss. Surges can enter the building through power lines, telephone lines, or data cables, and can damage or destroy sensitive electronic components. Thirdly, in residential homes, surge protection can protect appliances, computers, and other electronic devices from surges that can damage them or shorten their lifespan. Surges can enter the home through power lines, cable television lines, or telephone lines, and can damage or destroy electronic equipment. In all of these scenarios, the installation of surge protection devices can significantly reduce the risk of equipment damage and downtime, saving money and improving the reliability of electrical systems. It's also important to note that surge protection is not a one-time solution. Surge protection devices can degrade over time, especially after repeated exposure to surges. Therefore, it's essential to periodically inspect and test surge protection devices to ensure they are functioning properly. The frequency of inspection and testing depends on the environment and the expected surge activity. In areas with frequent lightning strikes or other sources of surges, it may be necessary to inspect and test surge protection devices more frequently. In conclusion, PIN insulators and surge protectors are both essential components of electrical systems, but they serve different purposes. PIN insulators provide electrical isolation, preventing current leakage, while surge protectors absorb voltage spikes, protecting equipment from damage. In the described scenario, the new design with surge protectors is more robust and provides additional protection against voltage spikes compared to the old design that relied solely on PIN insulators. Proper selection, installation, and maintenance of surge protection devices are crucial for ensuring the safety and reliability of electrical systems. Consider the grounding and bonding requirements of the surge protection system. A properly grounded and bonded system provides a low impedance path for surge currents to flow to ground, minimizing the voltage stress on protected equipment. Refer to the NEC and other relevant standards for guidance on grounding and bonding requirements. Also, think about the coordination of surge protection devices. In some cases, it may be necessary to install multiple surge protection devices in a coordinated manner to provide comprehensive protection. For example, a whole house surge protector can protect against surges entering the building through power lines, while individual surge protectors can protect sensitive electronic devices at the point of use. The surge protection devices should be coordinated so that they work together to effectively divert surge currents to ground. Another aspect to consider is the impact of surge protection on equipment warranties. Some equipment manufacturers require the use of surge protection devices to maintain the validity of their warranties. Therefore, it's important to check the warranty requirements of the equipment being protected and to install surge protection devices that meet those requirements. Moreover, keep records of surge protection device installations, inspections, and testing. These records can be useful for troubleshooting problems, tracking the performance of surge protection devices, and demonstrating compliance with electrical codes and standards. The record should include information such as the date of installation, the type of surge protection device installed, the location of the surge protection device, and the results of any inspections or tests. Consider the use of surge protection device monitoring systems. These systems can provide real-time information about the status of surge protection devices, allowing for proactive maintenance and replacement. The monitoring systems can detect when a surge protection device has been damaged or has reached the end of its lifespan, allowing for timely replacement to ensure continuous protection. Take into account the environmental conditions where surge protection devices are installed. Surge protection devices should be selected and installed in accordance with the manufacturer's recommendations for environmental conditions such as temperature, humidity, and exposure to corrosive substances. Extreme environmental conditions can degrade the performance of surge protection devices and shorten their lifespan. Finally, remember that surge protection is an ongoing process. As technology evolves and electrical systems become more complex, it's important to stay informed about the latest surge protection technologies and best practices. Regularly review surge protection strategies and make adjustments as needed to ensure that electrical systems are adequately protected against voltage spikes. The initial decision to upgrade from a transformer bank to a single pad-mounted transformer is a common one, often driven by factors such as space constraints, improved efficiency, and reduced maintenance requirements. The original transformer bank, composed of 3 single-phase transformers, likely occupied a larger footprint and required more frequent maintenance checks compared to a single, integrated 3-phase transformer. By transitioning to a pad-mounted transformer, the physical space required for the equipment is reduced, and the overall system becomes more streamlined. The decision to use underground primary feeds for the new transformer represents a further improvement in reliability and aesthetics. Underground cables are less susceptible to weather-related damage, such as from wind, ice, or lightning, and they also eliminate the visual clutter of overhead wires. However, connecting the underground primary feed to the existing overhead primary distribution system requires careful consideration of surge protection, as mentioned previously. The surge protectors are installed at the transition point to mitigate the risk of voltage spikes entering the underground cable and damaging the transformer. The partially underground distributed secondary design also offers several advantages. By running some of the secondary conductors underground, the risk of accidental contact with overhead wires is reduced, and the overall system becomes more aesthetically pleasing. However, it's important to ensure that the underground secondary conductors are properly sized and protected against physical damage, corrosion, and moisture. The selection of the appropriate surge protectors for the new transformer installation is critical. The surge protectors must be rated for the voltage and current levels of the primary system, and they must be able to withstand the expected surge currents without failing. The surge protectors should also be selected based on the type of grounding system used, as different grounding systems require different types of surge protection devices. In addition to surge protectors, it's also important to consider the use of other protective devices, such as fuses and circuit breakers, to protect the transformer and associated equipment from overloads and short circuits. Fuses and circuit breakers are designed to interrupt the flow of current when it exceeds a certain level, preventing damage to the equipment. The fuses and circuit breaker should be sized appropriately for the load and the capacity of the transformer. The installation of the new transformer and associated equipment should be done in accordance with all applicable electrical codes and standards. The NEC provides detailed requirements for the installation of transformers, surge protection devices, and other electrical equipment. Compliance with the NEC is essential for ensuring the safety and reliability of the electrical system. The installation should be performed by qualified and licensed electricians who are familiar with the requirements of the NEC and other relevant standards. The electrician should also be trained in the proper techniques for working with high voltage equipment and surge protection devices. After the installation is complete, the system should be thoroughly tested to ensure that it is functioning properly and that all protective devices are working as intended. The testing should include insulation resistance tests, voltage tests, and current tests. The results of the testing should be documented and kept on file for future reference. Ongoing maintenance is essential for ensuring the continued reliability of the transformer and associated equipment. The maintenance should include regular inspections, cleaning, and testing. The frequency of the maintenance depends on the environment and the operating conditions. In harsh environments, more frequent maintenance may be required. The maintenance should be performed by qualified and licensed electricians who are familiar with the equipment and the maintenance procedures. In summary, the conversion from a transformer bank to a single pad-mounted transformer with underground primary feeds and partially underground distributed secondary conductors offers several advantages, including reduced space requirements, improved reliability, and enhanced aesthetics. However, it's important to carefully consider the surge protection requirements and to select and install appropriate surge protection devices to protect the transformer and associated equipment from voltage spikes. The installation should be done in accordance with all applicable electrical codes and standards, and ongoing maintenance is essential for ensuring the continued reliability of the system.